Okay. Okay. Can we start the next session? Yeah, next session is technical operation part 2. And we have a whole speaker of this topic. And each of the presentation is a very important topic for the network operator, I think. And the first speaker is Matt Jensen, who is come from Facebook.
Hi guys, still pretty empty in here, but I guess I get started anyways because I've just been told my presentation time has been reduced. So I'll try to rush this a little bit. Do we have a thingy to actually do the slides, or do you guys do that remotely? Thanks. Oh, I got one now. So what I want to talk about today is, in front of this really big audience, is how we kind of arrived at where we are today in terms of how we build our backbone, how we connect people, how we build our network. This map is something I really like because this is not actually a network map. This shows connections between people. So this is literally every point, every line on here is people interacting with each other. So this really shows where people use Facebook and how people literally all over the world interact with each other. So this is really beautiful. As you can see, there is 2 billion people on there. So this is a lot of traffic. Most of you guys are network operators, so you know what that means in terms of getting those bits to the actual people wanting to connect. Now, every user on this network needs to essentially, at some point, end up at one of our POPs, right? It's like all those people with their mobile phones nowadays, mainly, they end up connecting to one of our POPs. And there's 2 categories of traffic really here in terms of networking that we need to distinguish. We have dynamic traffic. That's literally stuff that changes in real time, and therefore it needs to go back to one of our POPs. That's like your newsfeed, like the actual contents, what you're gonna get presented. That's the like somebody liking your status, that's messaging, status updates, stuff that really happens in more or less real time. And then there's static stuff. Static stuff is the actual like elements of the site, but more importantly, videos and pictures. And that stuff can be cached. By volume, that's the vast majority of the traffic, but both elements are obviously necessary to give a good user experience. So this is a snapshot from 6 years ago. We had a bunch of data centers in North America and nothing else. If you were in North America, that was pretty good for you. The further away you got, the less pretty this becomes. So this is literally showing latency. You see all the kind of darker parts here. That was not the best experience for the people in those places. So what we started to do is we deployed POPs around the world. So when you see here, this is like a user in Asia connecting to what at that point was our nearest data center in Oregon. You have like 150 millisecond round trip. But what actually happens? Well, the site uses HTTPS. So there's actually quite a few round trips that happen here before the user actually sees anything. So you have that first just TCP handshake. That's 3 ways going back and forth. Then you have the whole SSL back then, now TLS kind of session being established. That's another whole bunch of round trips. And then you have the actual content getting to the user. So at this point, we're talking about more than half a second till the user actually sees the element of the page, the picture, the frame, whatever. So this is actually not what you want to do, right? So as a first step, what we started to do is we deployed POPs around the world. So this POP somewhere in Asia terminates your TCP connection. At that point, that TCP handshake and that SSL handshake happen with a much, much shorter round trip time, while the actual element then still gets fetched from our data center. So we now reduce this 600 milliseconds to 240 milliseconds. So that's already a pretty big win, but that was only the first step. The next thing we did is we started deploying caches. So the cache can obviously only store static content. The dynamic parts still go through our POP. But for that static content, which is the majority of what you actually see, that's all those pretty pictures and videos in your newsfeed, that now reduces another significant amount, and we're going down to 40-ish milliseconds for that. So now we're talking actually really good user experience. And that's becoming more and more important, right? This is kind of like showing the evolution. If you looked at a Facebook news feed, for the older people in here, 10 years ago, that was basically all text. That was literally status updates in text form, with maybe 1 or 2 pictures from time to time, but it was text-based. This has completely changed, right? I mean, nowadays, at least in my personal case, it's pretty much all pictures. There's 1 or 2 lines of text in between, but it's all pictures. And for people younger than me, it's all videos, right? I mean, I hardly ever post any videos, but looking at our traffic stats, I'm definitely in the minority there. The actual vast majority of content on Facebook nowadays is actually video traffic. And by volume, that's obviously orders of magnitude more traffic you were talking about here. And this is not going to stop. I mean, this is going towards the virtual reality, augmented reality stuff, kind of elements of that we already have with the 360 videos we offer and stuff like that. That again is orders of magnitude more traffic. So this is really about how do we scale our platform to handle that, and for you network operators to actually be able to connect to it. So as a first step, we really need to address the shortcomings of BGP in that regard. The first iteration of our network when we built it was a whole bunch of POPs around the world. They were just a full BGP mesh, RAS 32934. That's how we serve traffic. And that was okay as a first step, but I mean, you very quickly hit the shortfalls of that. Because how do you decide where to serve the end user from? Well, essentially, you want to serve them from the POPs that's closest in terms of latency to the user. So what we use internally is something we call sonar. It's literally measuring latency from the end users to our POPs and caches, by the way. And built on that, based on that, we basically build a map and decide hey, for this end user, this POP is the best POP, and this is the second best, and so on. Initially, when we first did that, it was DNS-based. Nowadays, it's actually end-user prefix-based, not DNS anymore, but the principle is still the same. So then we decide hey, this is the best POP for this end-user prefix. And that allows us to get stuff served in the best possible way. Best possible way here means if we rely on pure BGP, we end up overloading links. It's BGP knows one best path, and if that best path has 10 gigs, but I have 20 gigs of traffic, we see that red line. That's not what we want to see, because that ends up with a pretty bad experience for the people using the site. So what we can do with this mapping based on latency is, as I said earlier, we have a best and a second best and a third best. So we can actually control it. We will not map more traffic there than we can actually map there, and then we go to the second best one. Now, based on that, the targeting can send the user to the best POP. That's a start, but that's only unidirectional. Routing on the internet is rarely ever symmetric, as most of you probably noticed. So what happens here, we targeted the end user to the best POP, which might be here in Taipei. Well, not here in Taipei, close to here in Taipei, not in Taichung. But the shortest BGP egress path might be in the US or in Europe, because BGP does not really care about actual physical closeness. It cares about network paths. So the one AS hop might not be in the closest place. I mean, Geoff mentioned that earlier. So what we did, we break up our network as the next iteration of our journey here. We broke up our network into essentially islands, so with locally significant BGP levels. So each metro, there might be one or more POPs in that metro, but each metro has locally significant routes. So now when we send that end user to that POP, the egress also goes out of that POP. It would not usually traverse the network to somewhere where there is a shorter BGP path at the other end of the world. That's, again, better. All of this is iterative, making it better than it used to be. So, again, BGP, well, we care about all those prefixes, local prefs, AS paths, MEDs, all those values. But in real life, what we're looking for is best user experience, right? So how did we evolve it beyond that? Well, we actually used BGP to overcome some of BGP's limitations. The way we did this, again, this was an iterative process. We started with like having that local router and having a link that we knew was full. So we have the link level data, we have a controller locally that gets all that information like the best AS path, the link utilization, and so on. So we know this link is full. We tell our box that, and we actually inject a BGP route into that router, diverting this traffic. In the very basic form, when we initially did that, that would just divert to transit. So we would go from that peer, link was full, we divert that prefix to the transit link on the same router, and we are not overloading it anymore. Again, great first step, but didn't stop there. The next iteration, what you can see here, there's two routers. And you see the second one is a peer, it's not a transit anymore. So we evolved that to actually go one layer lower and run this on our aggregation switches in the POP. And later actually in the whole metro. So we could divert traffic actually to a second peering link in the same metro with the same mechanism, injecting a BGP route into that aggregation switch, and then divert traffic to another peer. That already made it a lot better, but is that fixing the whole thing? No, this is literally a start. The whole philosophy behind this is it's an iterative process. We keep evolving, we improve it, and we can improve it some more. So here's some of the problems we encountered when we started doing that. So now we could divert traffic to another link by injecting that prefix. Great. But you have prefixes that have a lot of traffic. So if you look at CGNet, you might have 1/24 that has ridiculous amounts of end-user traffic behind it. Or if you look at IPv6, I mean, the whole beauty of v6 is that it summarizes very nicely. But that also means you have like 1/48 or 1/32 or something in a table that has a lot of traffic behind it. So if we have a link here that is overloaded and we move that entire prefix, then we didn't really achieve anything, because then we just have another link overloaded. So what we did here, we started like generating sub-prefixes in our locally relevant tables. So we break that big /32 here into a bunch of /48s that we can then divert one by one. So in this case, we would only divert a quarter of the traffic, but that's much more granular than that. So we can actually divert traffic to make the best possible use of available capacity, send as much of the traffic to the best path as we can, and only divert as little as we need to the second best path. Then another problem we started to encounter once we had this up and running in our platform is oscillations. And that's an interesting phenomenon. We had this local controllers on each pop, but we also had like the global controllers at the beginning I talked about that sent traffic to the pop that was closest in the first place. So what happened here is like we had the link being full, the local controller reacts really quickly, it's local, diverts some of that traffic to another link on the same box, all is good. But the global controller saw that same thing happening, but is slower to react and actually diverts traffic to another pop. So then that link is completely empty. Again, same thing, the local controller reacts, traffic is back on the link, all is good. And then the global controller reacts a while later and the link is overloaded again. And you end up doing that back and forth all the time. That's really not what you want to see. So how do we solve that? Well, we started to basically like completely separating those layers and making sure that the local controller really is only locally responsive and takes care of that traffic, and the global controller does not interfere in this. Another issue we encountered was like micro oscillations. We had traffic very rapidly going between two links on the same router or the same metro. That took us a while to figure out. What actually caused that was latency in our own network. When we first built this architecture, we had that controller architecture sitting on a box in California. Now, with more and more pops around the world, that wasn't fast enough anymore. So those boxes everywhere around the world reported to our controller in California, but by the time that took action, that was already too late, and we ended up with this horrible back and forth mapping of traffic because the steering signal came from a box in California at a point when it really wasn't relevant anymore. So to fix that, we actually made sure that we deployed those local controllers locally, so they were actually running in that pop to make sure they could react quickly enough within a time frame where that data actually became relevant. And then you see that picture on the right side, which is much more what you actually want to see. Having the best link utilized as much as possible and then overflow to the second best link with as little traffic as necessary. So I think I managed to kind of shorten this to roughly the time I've been given. Not sure I like talking that quickly, but here we are. This is kind of just a summary again to give you an idea what we're doing here, right? So we have a global controller architecture that really sends traffic to the best possible pop. And then as a completely separate layer within that pop, we have the local controllers that make sure it goes to the best possible link in that pop. So ideally sending as much traffic, perfect case 100%, to the direct peering with that network if we have it, and then as little as possible when necessary overflow to another peer that has that prefix or that company's transit provider. And the whole cache layer sits below that for a subset of the traffic, the static traffic, to get that even closer to the end user, using that same global controller architecture to target it there. That's it. I don't think I've ever done this presentation this quick. You guys got any questions? Well, it doesn't look like there is any, so I guess you got all your time.
Okay. Okay, thank you very much, Matt. Thank you very much. Next session is, thank you very much. And by the way, I forget my introduction. I'm a Shishutsu, coming from Japan. And as you know, Japan is sometimes impact to the from a disaster, like earthquake or typhoon. And the next session is presentation in disaster and internet routing. And the next session is Vardah and the route aftermath. And please come Anurag, Hurricane Electronics.
All right. So good evening, everyone. My name is Anurag, and I work at Hurricane Electric. We run a global backbone, and we are present across all the continents in most of the major locations. So today my talk is about Vardah and routing aftermath. Vardah was a cyclone which hit South Asia last year in December, and this talk covers around the routing changes which happened during that time when the cyclone hit. So some basic information about Vardah. It was a major cyclone impacting South Asia, so it was mostly India, Sri Lanka, Bangladesh, etc. I think there was impact on other countries around in terms of the internet infrastructure because of the cables, but in terms of physical impact, these were the countries which were worst hit. Almost 400 people lost their life, and there were damages worth more than $4 billion. So impact on the internet. There was a serious impact on these countries where there is lots and lots of overhead fiber, which a lot of the countries in the region are blessed with. And one impact was on the infrastructure around the overhead fibers. The other impact was on Indian operator Bharti Airtel's eye-to-eye submarine cable, which had a major failure during this period because of the cyclone, and that caused a serious impact. There was also an impact on one of the larger content players out in the region, especially in India, which resulted in choking of internet bandwidth across all major ISPs. The content player ASN starts with 1 and ends with 9, and that's one of the popular ASNs in the region, I guess. So we looked into the possibility of analyzing it from the routing noise on the impact. It is tricky to analyze the complete impact from the routing, because one is that a serious amount of routes are being announced from the core routers, and when there is a damage on the last mile infra, we don't see that being reflected in the routing tables. The other thing, even if we try to figure out which routes went offline, it's not doable from combined data like, say, Oregon route views or RIS, which is excellent data, but that's more of a aggregated data far away from the region. So the impact is, the visibility of impact is much lower. And so what we figured out eventually was that there was only one project which was doing it at a large scale, which is PCH. PCH has been putting up route collectors with AS3856 along with their DNS nodes everywhere, and those collectors collect the routing information from the exchanges. There are certain limitations onto that approach, and I'll come into that after showing up the data what we found. And so let's start with the data. So here is the routing announcement and withdrawals. This is for entire December. The impact time was somewhere between 10th to 15 December, with peak somewhere around on 13 December. And we can see there were serious amount of withdrawals visible on the route collectors. As you can see in the picture over here, this is route collector of PCH in APNIC Singapore, and this is for Hong Kong. We looked into the 4 exchanges for this study. So we covered Equinix Singapore, Hong Kong, HKIX in Hong Kong, and we looked into DECIX in Frankfurt as well as AMS-IX in Amsterdam. So 2 key exchanges on the western side, 2 key exchanges on the eastern side. So as I said, the route withdrawals were visible. We looked into the dumps to analyze it. So there were two key data which we looked into. One was the withdrawal information, which is available in the form of BGP dumps, and the other information was show IP BGP dumps in the text form which PCH publishes. So for the entire month, there were around 44,000 dumps per exchange. So we scripted around them and tried to map the prefixes, map the ASNs which had the maximum withdrawal and maximum noise across these. And we also did the mapping of each peer announcement in terms of to find how much announcement changed across the top peers. Again, we can't present the entire data in these slides because it would be like lots and lots of ASNs. And we picked the few top ones which had the largest impact. So this is how it looks like. This is route collector in APNIC Singapore. It saw a major downfall around that time. This is 12th, but remember, I believe this is in UTC. The time would be in UTC. So it was around this time when it saw a major downfall. In HKIX, there was a major downfall. It went up a bit and then again major downfall. I'll come on to this graph in a few minutes. In case of Frankfurt, sorry, for the TechX in Frankfurt, we actually saw an increase in announcement exactly around that time frame. And in case of AMS-IX, there was a much higher announcement. It showed in some noise around there, but the announcement clearly increased during this time. So having a closer look at APNIC Singapore, this is how it looked like. So these are the top ASNs. Oops. These are the top ASNs which showed withdrawal or announcements. So AS6762 Telecom Italia, there was the announcements actually went down a bit and then increased for a while, and then there was a major downfall around this time. For AS3491, which is a major operator in the region, which is PCCW Global, there was a major withdrawal and it continued for entire month. And this part is quite obvious because once you have a submarine cable outage, it takes a while for things to get fixed, and possibly these networks would have rerouted the traffic because we are graphing only from the exchange. It doesn't mean that they had a full outage in their network. It just means they were rerouting across these. They were disconnected from the exchange, or they had actually lesser capacity, which is why they removed a significant chunk of their prefixes. Or it could be even their downstream being disconnected from them. There is AS6939, which happens to be Hurricane Electric, the company I work for. We had an increase in announcement during this time, and then there was a downfall. It increased for a while based on certain downstreams who were trying to reroute across during this problem. And then AS9498, which is Bharti Airtel from India. They had a full outage during this time. The prefix announcements went to 0 and then slowly increased, but it was still much less, actually less than half of what it was originally by the end of December. So clearly there was a big impact on the routing tables during the Vardah. Then some of the other top ASNs, AS1273, Cable and Wireless, or Vodafone Global now. They had a jump in the route announcements after a short downfall, giving a sense that some people might be using them as a backup provider. AS4826, another large ASN, they had a major downfall. This graph is really very interesting. I kind of find this graph very cool. This is Reliance Communication or GCX or Flag. And they had a major downfall and they immediately recovered it somehow. And that's very cool. They were able to reroute across and continue almost in maybe less than 24 hours. This one, I put it intentionally over here. This does not belong to the logic which we put of the top ASNs which had the noise. This belongs to a large operator in the region, a very large operator from India, which is Reliance Jio. They just launched their services and they have been growing like hell. And so in their case, the impact was almost no. They had the prefix announcement increased during the start of the month, showing that they had a new submarine cable, which is Bay of Bengal cable, just lighting up. And they started using BBG. But beyond that point, they were not impacted at all. They were not using possibly I2I during this time or any other cable which was impacted. So 196 ASNs are visible at the IX. When I say 196 ASNs are visible, I mean to say these are the ASNs visible to PCH route collector. There are way more ASNs at Equinix Singapore, but their data is just not available. I'll come on to that limitation in the end of slides, but it's important to note that what is visible is there for sure, but there can be a lot of things outside the visibility because routing table is not just visible from them. Major ASNs, as I already said, a few pulled out, and going ahead with HKIX in Hong Kong to see if there is any similarity. And it is important to note that a lot of ISPs in the region connect to Hong Kong from either from Singapore or other ways around. So a significant traffic flows from that location. So the impact was quite visible and similar. So again, we have PCCW Global AS3491 having reduced number of routes, either they're on or possibly they're downstream routes. We had a major jump in AS4635, and I find it very fascinating. This ASN belong to HKIX route server, and it would be interesting to hear from someone from HKIX on what resulted in this increased route flow. One possible reason could be the forced multilateral policy at the route server, which is why a lot of people were trying to use that as to read out the traffic, which is probably fair and fine. Then in case of AS6939, Hurricane Electric, our network, we saw increase in routes for certain time again, and then after that, certain downstreams were disconnected because of their own capacity crunches, and the announcement decreased significantly. They were almost able to recover it by the end of the month, as you can see in the graph. This again with the Reliance Communications flag, downtime or actually reduced number of routes, significant reduction for one day and then coming back. In terms of stats, this is based on 84 ASNs visible at the IX to the PCH route collector and top 10, we just posted over here. As I already said, AS4635, we are not sure on the number of increased routes over there. So where did the Asian routes go? If you're not following the scenario, then you may just ask that was there a full blackout or outage? While that's really not the case, people were able to read out, and it actually still worked with poor performance. So here we see the graphs for DECIX Frankfurt. We see that one of the top ASNs in the entire list was AS3257, which is, I believe, GTT or TINET's network, and we saw a large number of increase in the routes it was announcing over there, and then it went down. And it's important to note, I don't believe they are at the IX fabric in terms of the peering fabric, but I think they are peering with the route server, so it's good to see their stats. There was an increase in our number of routes again for similar reason, that people from east starting routing via west, and they started doing more specific announcements. So there was an increased number of routes during that time for the same reason, and it actually stayed up for a significant time during the month, as they were probably using us as a backup for rerouting across the other capacity. For AS6762, which is Telecom Italia, there was a relatively reduced number of routes beyond this point, indicating that some of their downstreams were disconnected. And same for AS3491, which was quite severely hit, which is PCC here. And we see a significant drop in routes, possibly because of disconnection of the Asian network with the European counterpart. AS1273 increase and then decrease. AS6461, which is above net, slight jump around this time, and it stayed for a while. And we did not graph it for 2 or 3 months, but I'm sure the graphs would be at their original level after this time, maybe except in certain cases where someone might be very much pissed off their transit providers and might be just switching away, which would be an interesting thing to see actually. AMS-IX at Amsterdam. So at Amsterdam Internet Exchange, again, increase in number of prefixes being announced by TINET, increase in number of prefixes for a short time by Hurricane Electric, a significant increase in number of prefixes by Bharti Airtel because of the disconnection or capacity crunches possibly in the East Asia. So what they were essentially doing would be to announce more specifics out in Europe, and getting a lot of Asian traffic getting rerouted via Europe. So instead of Singapore traffic hitting India directly, it would be Singapore flowing all the way up to US, coming back from Europe to Asia. And AS6461 above net, significant jump around this time, and it stayed up for a while, possibly because of some downstreams over there. We're using them for backup or some emergency capacity. For Reliance flag, while we saw that they had reduced number of prefixes for a while and it immediately came up, we can see there was a significant jump in their announcement across the same time. The announcements went up all the way from here to this point, and it just stayed up over there. Possibly because of the downstreams again, because most of these are the backbone ASNs and announcing very little on their own, originating very little on their own, and it's mostly their downstream customers doing that. AS10026, which I believe Telstra, PACnet, right, it just went down for a while, and the announcement stayed down, indicating that they might be on one of these submarine cables and having the impact. Telecom Italia, again, a downfall as we saw in the other graphs, and PCCW Global, as we can expect, a major Asian player getting relatively disconnected from this part of the world. Some of the conclusions. So cyclone and natural disasters do show their impact on the routing tables, and there would be a lot more impact on the ground infra, because I come from India, and I have seen networks staying down in Chennai, Bangalore, and nearby regions, because this was a hell lot of overhead fiber which was disconnected. But it's just hard to statically analyze that, because we don't have any project doing that at this phase, except maybe RIPE-ATLAS, but then the number of active RIPE-ATLAS probes is still not optimum. It's somewhere around 53 right now in India, and we are trying to increase more and more probes to have better visibility. Maybe if something comes up in future, it might be interesting to analyze it with the Atlas to see the ground level impact, because even the route announcement may go back to normal. There could be end users still, staying disconnected. The router might just be originating the prefix with no traffic. As I already said, operators in South Asia try to reach east via west and vice versa during these outages, and this was evident in a lot of trace routes, and we could see latency jumping up all the way from 100 millisecond to 300 or 400. And this impact was further aggregated by one of the largest content players going down, and a lot of upstream providers were having the problem in terms of capacity for that. And network pops in Asian networks with their pops in Europe saw a significant reduction, as we can see in case of PCCW and others. Some of the miscellaneous points, and this is very important, and I always stress on this, and Mr. Jeff Houston is in room, so I always try to stress more on this so that he doesn't come up and ask me about it. So this data is purely based on the route collector. What is visible is there. There can be more things outside of the visibility view. What is visible is definitely there, but there can be some other networks, maybe from these regions, showing completely opposite view of the thing, and we just can't map them out. It's not possible, because if we look at the aggregated dumps, it just makes no sense. We don't see any of the noise out in, say, Oregon route views, or some of the RIPE collectors out in Europe. And most of these jumps, we actually looked into the routing table. These were because of more specific announcements. And as you can see from the first graph I shared, not a lot of withdrawals happened. Withdrawals were there significantly, but that was mostly when the networks were physically getting disconnected. I don't believe they were there because networks actually pulled out the routing information. They just started announcing more specific to balance off the traffic. And PCH POPs in India and Bangladesh were ignored. So I think Ajay from MCH is Mumbai IX now probably is here, and they also have a PCH POP out there. And I looked into the routing noise on these exchanges. It was just almost zero. So we did not publish them over here. Most of these exchanges stay as the local exchange, so there was no visible change in the international traffic. The only thing which we saw somewhat was one of the content players going down, and then a lot of withdrawals from that in terms of those routes. But there was absolute zero impact from Vardah on these, which also tells you why local exchanges are important. So I'm up with the time. Oh, okay, so I'll try to just wind up, and I'm pretty much on the last slide. So this is the PCH raw routing data. You might find it very useful. One thing I love about it that it has the BGP dump style dumps for the withdrawals and announcements. But yeah, it is for specifically for the routing table, it's still show IP BGP, so it's a little bit tricky to parse. You need to write something around it. One of the news article just telling about the internet slowing down and the BGP dump tool from RIPE, which you can use to analyze the tables. That's about it. Thank you.
Thank you.
Any questions?
Thank you very much. I'm sorry, our time is very limited, so we cannot accept it question time. So if you have any questions, then please contact the analyst. Thank you very much. Next session is rapid detection of BGP anomalies. Please.
Good afternoon, everyone. My name is Vardah. I'm PhD candidate at Amsterdam University of Technology. So today my talk is rapid detection of BGP anomaly. So again, we will have another talk about BGP. So let's start with BGP, my outline of BGP. So a brief discussion, what about BGP, the challenges of detecting BGP anomalies, and then I will introduce my detection tool, which is based on using RQA scheme. Then evaluation of my scheme, then how we developed my scheme to be a real-time detection anomaly tool, and then I will conclude my talk. So BGP anomaly. Before starting with BGP anomaly, let's have a brief fundamental. Yes. Let's have a brief fundamental about BGP. What is BGP? BGP is the border gateway protocol which is responsible for managing network reachability information between autonomous systems, where an autonomous system is a set of router and a single technical administration unit using interior gateway protocols such as OSPF, ISIS, and DRIP. And these autonomous systems communicate with each other within inter-domain using gateway protocol. So BGP is an incremental protocol where after a full exchange of routing information base, just routing updates are changed to show the network management change in the underlying system or in the topology. So briefly, when there's no change in the network management, we should not see any BGP updates transferred between autonomous systems. However, this is not what we can see in real BGP traffic, where there are lots of autonomous systems or set of autonomous systems send an announcement followed soon by withdrawal that does not appear related to underlying management change. And you've hosted actually at Vardah a weekly report for the most unstable autonomous systems, so you can see which autonomous systems are sending all the unstable BGP traffic all the time. So it's really difficult to define what is meant by BGP anomaly, because there is a set of autonomous systems that send unstable traffic all the time. Okay, we define or we classify BGP anomaly into two main types. We define BGP traffic as unstable BGP traffic, and then we define another type of BGP traffic as anomalous BGP traffic. Anomalous BGP traffic can be categorized as well into different types. Into a single BGP update can be classified or categorized as an anomaly if it contains an invalid autonomous system, or it can be defined as an anomaly if it contains invalid or received IP prefix, or a prefix that announced by illegitimate autonomous system. While a set of BGP traffic can be categorized as anomalous traffic if it shows a rapid change in the underlying BGP traffic or the number of BGP updates over the time, containing longest and shortest AS path, and changes in the behavior of the total BGP traffic over the time. Our interest in this research is detecting BGP anomaly for a set or for a set of BGP updates and over the time. So BGP traffic has been categorized as a complex, noisy, and voluminous, where BGP speaker can generate up to gigabyte of BGP traffic per day. This is an example that's showing BGP traffic sent by the Peer Autonomous System 1972-64 at Route View project. So you can see how it's noisy and it's complex to identify BGP anomalies within this set of BGP traffic. So, our interesting to detect BGP anomaly, we need to differentiate between the unstable BGP traffic and anomalous traffic. So we need a technique that can rapidly detect or differentiate between these type of anomalies, where last statistics show 20% of anomalous traffic can affect 90% of the internet in less than 2 minutes. Furthermore, to apply or to deploy a real-time BGP anomaly detection, we need a technique that can be applied or deployed in a light way and in real-time mechanism. So detecting BGP anomaly using RQA. So before starting to describe what is RQA, we model a BGP speaker as a dynamic system using the concept of phase plane. What I mean by phase plane, we look to the system as a multiple dimension on different time states. So for example, this is a very simple example for damped oscillator system. This oscillator system is changing over the time, so you can see here actually how this system can be shown in the phase plane trajectory. For a more complex system, this is for a chaotic system, and the weather can be classified as a chaotic system. So here you can see how the system can be changed in different dimensions, going from this state to another state on different time. So the outcome of our modeling, we identify BGP speaker, which are the router or device that run BGP, as a deterministic system, stable, linear, and recurrent. I'm not going to describe each of these characteristics individually, but for simplicity, that means the BGP speaker, the BGP router can be identified and can be predicted because of the characteristics of recurrent and deterministic. Based on our outcomes of our modeling, we introduce our novel technique, which is called recurrence quantification analysis, an advanced linear statistical analysis based on the concept of the phase plane. RQA has multiple measurements. Each of these measurements measure the characteristics of the system over the time. So for example, for the RR measurement, it's the probability that a system will recur after n time. While TT, it's measured for how long the system it's remain in a specific state, and the third measurement, which is T2, which measures the time taken to move from one state in the phase plane to another state. So to describe that with a simple example, this is shown to you, This is showing to you a recurrent system or recurrent time series data that exhibit of changing of the value of 1, 2, 3, 4 in such a way that show recurrent behavior. The corresponding value for this system or for this time or the output of that system can be shown here, where you can see there is no significant change in the value of RQA measurement. Now, what happens if we change a little value that is between 1040 to 1060 when change the amplitude from 1 to 3? Now we can see that RQA measurement can detect the change in the underlying system. Although it is difficult to identify that by looking to the data, it is possible to detect that using RQA scheme. Now let me describe the design of our detection scheme. So the input of my detection scheme is a series of BGP traffic sent by the BGP speaker who is intended to be monitored. Then we calculate BGP feature. We focus on two main BGP features, which is the number of BGP volume. When I say BGP volume, that means number of announcements and withdrawal per second, because we are looking to detect BGP anomaly if it's happening per second at that second. Then we calculate RQL measurement for each of these BGP features individually per second again. So here, for example, if at time, for example, I, we can see, I'm not sure why actually here is changed. It should be the I plus W plus 1 should be here. Anyway, sorry about that. Okay, so we measure every second the characteristics of BGP features with the previous W window. And this window is changed, is increment by time. This mechanism is called sliding window. And the output of this stage is the RQA measurement in terms of TT and T2 for each BGP features. Then we apply another technique to calculate the significant change in the RQA measurement. So the output of the moving average will be multiple alarms per each RQA measurement. And finally, the detection is simply logically or for the all RQA measurement alarm. So now, based on the past well-known BGP event, there is a lack of ground truth information of the timestamp. So for example, what is the nearest time in second for a BGP event that has been started before or started before? And we need a control test bed so we can evaluate our result. For that reason, we use a BGP control test bed, which is based on using Vardah, which is Virtual Internet Routing Lab, a software produced by Cisco. And we developed a tool which is called BRT, a tool to replay past BGP update with a timestamp. This tool has been evaluated and tested using different router operating systems, such as real Cisco router, Vardah, and Quagga. And it supports IP version 6 and pairing as well. So this is a simple test bed topology that we use by injecting the past BGP update on autonomous system number 14. Then we monitor the BGP traffic at different vantage points. So after time 2950, we introduced an emulated hardware failure by shutting down all the interfaces at autonomous system number 1. Now, this is what we monitor, or this is the output during our control test bed. So the neighbor of the autonomous system number 1 cannot recognize the failure because of the hold time, and the hold time value is 180. So as you can see, during this period of time, the autonomous system number AS21 cannot recognize the hardware failure, then start to recognize the hardware failure by sending BGP update for the announcement and alternative path. When we measure the RQA measurement for these BGP features, we can see that RQA measurement can identify this failure. Now, let's evaluate our RQA scheme using past BGP events based on the data that we get from our control test bed. So there are 4 parameters that we use for our detection or the evaluation of our RQA scheme. These parameters are true positive, which represent number of anomalies that are truly classified as anomaly, and true negative represent number of normal events that are classified as normal. True false positive, number of normal events that classify as anomalous, and finally false positive for number of anomalous events that are classified as normal. Our interest, or the most important 2 parameters, is the false positive and false negative, for their effect on the network operator or provider, or to getting a lot of false alarms or missing real anomalies. So we test our RQA scheme on different types of BGP anomalies, such as denial of service attack that's happened by NIMDA attack, TTNet as a type of misconfiguration, and TMNet as a type of misconfiguration, and Moscow blackout. So here it is an example for our detection scheme. How can RQA detect the anomaly for the TTNet? Here we can see that RQA can detect 1, 2, 3, 4, 5, 6 alarms during this event. So going further to see what's going on. So RQA can detect hidden anomalous behavior that may pass without detection. So for example, the peer autonomous system stops sending BGP traffic during 2 minutes. And before these 2 minutes, and after these 2 minutes, you can see there are different frequency of sending BGP traffic. Another example here, which is a little difficult to detect, you can see that autonomous systems send different frequencies. So here start to send BGP updates every 30 seconds. Here, then after a while, we can find that this peer sends BGP traffic every 1 second. So the evaluation, or in summary, the evaluation of our scheme, we can find over 2 weeks of BGP traffic that RQA can detect all the possible BGP anomalies with an average rate of 1 false positive every 42 hours, 0.8. Now, we developed our scheme to be a real-time tool. So for real-time tool, we need a real-time monitoring for BGP traffic. For that, we developed a tool which is called BGP Collector. Once again, it's based on using NetBGP, a module of Perl. And, and we evaluate past event. So we download BGP traffic that's related to TMNet event, re-inject this event with the timestamp using BRT, then monitoring or detecting BGP anomalies using our tool, which is RBAT tool. Here it is, during 2 hours of anomalous BGP traffic, we can see that RBAT tool can detect 3 types of anomalies, or 3 alarms. These alarms, as you can see, the first one is generated by high volume of sending BGP updates, which RQA tool can detect that within 2 seconds. Another period of anomalous attack that can be detected, here you can see, once again, there are different oscillations of sending BGP traffic. Here, for example, sending BGP traffic every 30 seconds. Here we can see sending BGP traffic every 2 seconds. Wait for 30 seconds, once again, send every 2 seconds. So to conclude my talk, so BGP is vulnerable to different types of attack. Detecting BGP anomaly is a challenge. We need a technique that can differentiate between unstable BGP traffic and anomalous BGP traffic. We introduce our IQA scheme, which is a novel scheme based on using phase plane concept to detect BGP anomaly. RQA can rapidly detect BGP anomalies. Furthermore, RQA can detect hidden anomalous behavior that may pass without detection. And finally, our RQA scheme can detect BGP anomaly with 1 false positive every 42 hours. I would thank APNIC for giving me the opportunity to develop my approach to be a tool. So part of this of my presentation, which is the BRT version 2, and the detection tool is funded by APNIC. I would also want to thank viral team at Cisco for providing free license and support. And this is some useful links. So the first one is the website for our project. And this is some publications that show the modeling and the detection technique. Thank you very much.
Thank you very much. Do you have any question to there? Can I ask one question?
Sure.
do you know the 25th August Google misconfiguration
By Google?
program? Yeah, by Google.
By Google, yeah.
Can your system can detect the similar problem?
So my understanding for Google, can I just show, go back. So, anyway, so my understanding for the Google incident is a type of BGP misconfiguration. And my technique has been applied to two different types of BGP misconfiguration or the loud leak, such as the TTNet or TTMnet. So it should actually can able to detect that. But as I said before, our interest is to detect BGP anomalies in a series of BGP traffic, not in a single BGP update. So our technique cannot be able to detect hijacking, okay? Such as the Linksys incident that happened in Europe 3 years ago, 4 years ago.
Okay, thank you very much.
Thank you.
Yeah, thank you very much. Yeah, the last session is Jeff Houston, and he explained some NAT history, and as you know, the APNIC area already IPv4X houses. So many Japanese service operators already deployed CGN carrier grade NAT. So this topic is very important, I think.
Afternoon, all. You know, it always amazes me the myths we tell ourselves that doesn't and don't withstand scrutiny. Domain name certificates add to the security of the internet. What a load of crap. They don't. They're a thin veneer that actually adds nothing to security. Another myth we tell ourselves is that NATs are evil and horrible and should go away. And, you know, I find it really hard to agree with that. I think it's actually wrong that NATs actually are something entirely different. And to make the case, I'd like to actually go through where we came from and where NATs arrived from, and actually why I think they're actually underappreciated. So first up, this is not a deeply technical talk, or if it is, it's more about architecture and design of networking rather than bits and bytes and protocols. So, you know, let's cast our mind a little way back to why the internet was so radically different from anything else that was around as a networking technology. And the major reason, I think, was actually the TCP part of the IP protocol. Almost every other networking protocol at the time used reliable gateway-to-gateway transfer. So every intermediate switch sent the next thing a packet and then waited for the next switch to go, yeah, I got it, before they give it up. We didn't realize at the time, but that was the reason why most protocols were hideously inefficient. You know, X25, for example, because that gateway-to-gateway handover absorbed a huge amount of time and nothing ever went quickly. TCP was kind of this amazing cut-through that said, let's not do that. Let's make every packet an adventure and just use an end-to-end flow loop to actually make things work. So all of a sudden, two concepts emerged from that. One, you needed end-to-end addressing, and two, you pushed all the functionality out to the edge. They were the revolutionary bits. That was the true reason why this kind of took on. Why? Because it stripped cost. All of a sudden, you can make really cheap networks work, and that was pretty cool. All the responsibilities on the end host. The network operator didn't pay for the end host, you did, so that's your problem. So cost was stripped out and everyone was happy. This is the way it worked. So the architecture you can actually see in the IPv4 header, because each header of a packet had just enough information to send it one hop further. So there's a version number, you know, I'm version 4. There's a time to live, which was put there because you didn't want packets living forever, you know. Eternal life is not given to IP packets, Everyone who touches that packet decrements it. When it hits 0, kill it. The header checksum, not obvious, but you know, at the time it seemed like a good idea. And the destination address, where am I going to? Interestingly, you could argue the source address wasn't necessary. The network never needed to know where the packet came from. None of its business. IPv4 networks were basically one-way networks. And so the standard model, and you must have seen this if you've done any kind of networking, was that as you passed a packet into the network, the intermediate switches were never meant to look at the transport header. Never. They were just looking at the IP header and making destination, switching decisions based solely what was in the IP header. You could fragment it on the fly if you wanted. You could drop them if you wanted. That was the whole idea of an internet. The addressing was end to end. As the packet left the source, the address was of the destination. Okay, good things. Unlike X25, even ATM and all those other kind of virtual things, unlike MPLS, unlike SDN and all the other bits of stuff du jour that we see today, unlike most of that, this stuff is incredibly efficient. No setup, no teardown, nothing like that. No symmetry between forward and backward flows. The forward flow can go through entirely different gateways than the reverse flow. It would be good if you didn't shuffle the packets, but not mandatory. If you really want to change the packet order, feel free. Because the end-to-end transport and the hop-by-hop forwarding in IP is purely decoupled. The transport, protocol option is a host choice, what a network choice. If you compare that to the networks you operate today, how many of those things are still true? You're running MPLS, aren't you? Oh shit, that's set up and tear down. God, you're running some kind of RSVP-TE. Oh God, you've enforced symmetry. Bugger. You're using some kind of ECMP. Shit, you better not reorder the packets because all hell will break loose. And quite frankly, you can only use TCP and UDP and nothing else. So actually, today's modern networks, it's a dead set loss. You do 0 out of 4 of these things. Why? I'm like, that was what actually made this stuff work really well. But I digress. IP addresses were globally significant unique identifiers, and every router needs to know where everything else is. That's what BGP is actually all about. So in this kind of addressing world, where every device has an address, the total number of devices is equal to the total number of discrete addresses. Yes? Yes. So back in August 1990, some of you might have even been born then, Frank Zielinski turned up at an IETF and said, oops, because I've been looking at stuff. You can tell it's from August 1990 because not only is that a transparency foil, it's handwritten. Because we didn't know how to print on transparencies until at least 1992. If you'd fed a foil into a photocopier in 1990, the drum would get all wet and sticky and no one would be any happier at all. So yes, you can tell it comes from that date. And he did lots of graphs and lots of maths, but the real thing was, by about 1994, the Class Bs were going to die. This was horrible, we needed to do something. It wasn't that we're running out of addresses, we were running out of Class Bs. So what we did as a result was introduce classless routing, which we use today. Though despite the fact that a lot of computer science still teaches Class A, B and C and so on and so forth, that is bullshit. Basically you carry the prefix with the route. This is what we do. And this kind of worked. We bought about 20 odd years, which we've been living. CIDR was heading us to disaster. We've actually managed to keep the routing table and the addressing system under control. Fantastic, aren't we good? But it only bought a few years, it didn't buy a lifetime. So all was going on was that mainframes were disappearing, personal computers were going on, laptops, mobile devices were just on the horizon, and the things of this world were obviously going to happen. And so the thinking was, given a range of possible choices as to a new protocol, the IPv6 decision was as conservative as it could possibly be. The only thing it really changed was the length of the address fields. It changed almost nothing else. It could have, but it didn't, right? So this was a very conservative origin. Expanded address fields. Interestingly, the other things they changed, I think, were mistakes. The change to the fragmentation control was about the worst possible way it could have been done, and today's networks in V6 handle fragmentation really, really badly. Thank you, vendors. You are so good at this kind of stuff. They also roll to the options and control fields again, probably badly. UDP and TCP unaltered, hop by hop destination unaltered, and the address plan was never quite specified, you know, oops. But V6 wasn't the only thing around. And I picked this because it's a nice example, but it wasn't the only one. John Crowcroft had a very similar one. This dates from May 1994, and it's one of the early descriptions of address sharing. Because there are other ways of extending addresses, and this is one that at the time was revolutionary, today is just what you do. A bunch of devices share a common external net, so that when they push their packets through the NAT, the address headers get transformed, out comes the same address for all of these internal devices. So that while you might have 10, 20, 100, 1,000 machines, on the outside you're one address for all of them. Very neat idea. And again, if you look at the way the header fields work, you actually take not only the source and destination address, but you reach into the transport header. You reach down in there and steal the source and destination ports. And you can use those too. You can use those too. Because what you set up is a binding table where you take the source and destination addresses and port fields and look them up in a table and produce a new one. Now think about this for a second. How wide is that table? You've got a source address, 32 bits, a destination address, 32 bits, 2 port fields, another 32 bits. That's 96 bits. So what you're actually using is a 96-bit pseudo address field, not 32 bits. All of a sudden, you've actually extended the useful address space used in these kinds of networks. Outbound packets, if there's no binding entry, you create one because you like them. Inbound packets, if you don't find a match, you get rid of it because that's unsolicited. So NATs certainly have an inside and an outside. But the operation, insanely simple. You change those 4 fields in red and recompute the 2 checksums. Total? 100 instructions? Not a lot. You can do this awfully quickly if you design the right table space. So this is not slow. It's really, really fast if you push it. As soon as this came out, and as soon as folks started doing it, because folk did start doing it. Why? Because the dial-up internet. You remember the dial-up internet? It was shit. However, there was one thing about that. When you dialed up, the assumption was there was one machine doing the dialing, so that your connection was to one machine. But quite frankly, if I had a computer, other people in the household had one too very, very quickly. So all of a sudden, it wasn't a machine dialing up, it was a network. How do you share one address with a network? You put a NAT inside the modem, inside the edge device. So these were really common at the time, yet at the same time, the purists were saying, look, I'm sorry, this is really, really ugly. Because the way the NATs work, outbound traffic and inbound traffic need to go through the same box because you've got to translate in both ways. Can't do that, can you? No. You need session state within the network. Yeah, okay, fair enough. It enforces a client-server architecture. Well, yeah, it's what they do. It's just what it is. I'm not sure that everyone wanted peer-to-peer. And in fact, the servers were happy being servers, the clients were happy being clients. Most of the networks we were building were hideously asymmetric. Huge amount of downstream capacity, very little upstream. If folk tried to be servers down in their houses, ISPs got angry because that was not the way it was meant to be. Servers were meant to be servers. They were meant to be in some high-cost data center. Only the clients were allowed out there in the field. So the fact that NATs enforced this, oh, that's terrible, was actually amazingly convenient. The idea that you had this middle box created fragility, all that's true. All of these criticisms are incredibly true. But at the same time, it actually led to a larger reaction, which I think was kind of a little bit hysterical. And in the IETF, the mantra at the time, whenever gnats were mentioned, was this chorus from the crowd that were going, gnats are not just bad, they're evil. They are so evil and should be discouraged so much that we refuse to standardise their behaviour. Which leads to, I suppose, the worst problem about gnats. Programmers should never be told to be creative. By your very nature, you're lousy at being creative. Totally shocking. And when you've given a lack of specification, you will find every possible outcome simultaneously. And so gnats with UDP behaved idiosyncratically. Different brands, different models, even the same model from the same vendor sometimes had different behaviours. You know who you are, Cisco. So all of a sudden, what we saw was a whole bunch of convoluted application behaviour in UDP to figure out the kind of mess that the gnats were doing because the IETF refused to standardise them. Because the IETF thought they were evil, it was almost a self-fulfilling prophecy that realistically the real problem was the lack of standardisation rather than any intrinsic vilification of gnats in their own right. But for all of that, you have to realise that what we've done today could only have been done with gnats. Some folk reckon there are 25 billion connected devices, and I have no reason to contradict that. I'm like, oh, it's just a guess, sure. And Statistica.com seems to think it's a good guess. No reason why not. 25 billion devices, 2.8 billion assigned addresses, that's what the RIRs tell us, of which around 1.8 are actually being used. So the address sharing ratio is somewhere between 10 to 1 and 20 to 1. So if there's any evidence of astonishing use of NAT, it's in these numbers alone. So how can something that keeps the internet alive be so evil? How can something that is so intrinsic and so common to all of us, like gravity is to our physical world, be considered evil? I just don't get it. Because if some ways gnats keep this internet running right now, it's as simple as that. Why? Because my decision to actually do one is independent of yours. It doesn't affect you. Each of these decisions are independent. When I put a NAT, nothing changes. They're backwards compatible. So I've got the two things that V6 can't do: backward compatibility and piecemeal deployment. They impair open peer-to-peer connectivity, which you happen to be Rupert Murdoch and his fellow travellers seems to be a good thing. Certainly much of the industry around copyright and IPR seem to think that peer-to-peer protocols are evil and intrinsically thieving bastards, so anything like NATs to disrupt this is obviously a good thing. I'm not sure I totally agree with it, but certainly that's what's going on. And in some ways the ISPs support this, that they too think this is a good thing. Enforcing client behaviours behind NATs is actually seen as positive. They invade the port space and actually limit the transport protocols. As I said, some folk really like that. And interestingly, they isolate the edge network from the carriage network. If there was one thing the telephone company did right as a monopoly and did so badly for us as consumers, it was insist that it owned everything, from the plastic handset, the wiring, the lot. You could not connect unauthorised equipment to their precious wires because they owned everything. There was no gap that said, that's you, that's us. Nothing. And they enforced that model for almost a century and created a monopolistic cartel that exploited all of us for so long it wasn't funny. NATs broke it. Because behind a NAT, it was open space. What you did in your homeland was your home business. You could connect anything you wanted. It wasn't something that required permission. There was nothing required as to what you did in the consumer world of your making. NATs were that air gap of control. And NATs were the sort of the chisel that broke apart the monopoly of the carriers. Because all of a sudden they didn't reach to your computer. They stopped at the NAT. And they could not reach further. They could not control what you put on there. They had no control over the devices you used and connected. Huge change from telephony. And that was a massive change in the economics of this business. Because all of a sudden it liberated us as consumers to competitive pressure. We were able to buy the cheapest and whatever we wanted, irrespective of what the carrier might have required us to do in previous generations. So that last thing was actually really critically important, and NATS enabled it. Okay, so how far do they go? This is Nanog earlier this year. He uses a single /4 for 7,000 customers. He seems to be doing just fine. I am totally impressed with this. This is nothing special. You can certainly take it further because it is 96-bit wide. And effectively, you can get, with single user port blocks, around 10 users to each address. If you try pooled overflow, you'll get up to 100. Most of you are doing this. I'm pretty sure most of you are doing pooled ports and getting around 1,000 users to every address. Again, that's not very hard these days. And if you go the full hog and actually do 4-tuple binding maps, use all 96 bits, you can get close to 10,000 users per single address. We have yet to really discover how far we can push NATs. And interestingly, the longer you delay in V6, the closer you are going to be exploring that bottom line, because that's the only way you can go. Like, you either push more people behind the address or you run V6. Your choice. But interestingly, V6 is not entirely the golden knight here. As I said before, it was never backward compatible, which gets us into this ghastly world of dual stack transition, which is going in fits and starts. Nobody can run an all V6 network until the last significant amounts of V4 have disappeared. And none of us know how long that's going to be. So this is a game that it doesn't matter how quickly you deploy V6, you're waiting for other folk to also deploy to the extent that you feel confident you can turn off 4. That's a difficult game, and no one knows how long that's going to last for. Does V6 have more usable address bits? Wow. If you give everyone a /48 as an end site, what do NATs give you? Well, it's 32 bits plus 16 bits, that's 48 bits. If I'm using 4-tuple binding, I could probably get about 52 bits. So it's not that V6, in its current way of usage, has heaps more bits. Because of the address plans, we wiped off the bottom 64. Oops, can't use that. And then we started doing in-site addressing around the 48-bit point. To be perfectly frank, the amount of usable address space for customers is not all that different from the maximal space you achieve with NATs, which is depressing. We have all these 128 bits and we're just thrumming them away. Is it more flexible? Geez, this is what I want to talk about in the next few slides, so I'll use this again when I come back to it. Is V6 cheaper? Well, obviously not. It's 2 protocols. This is not working too well. So the industry is adopting cheap, expedient, low-cost solutions wherever they can. That's just the way it works. It's called capitalism. And we'd planned this transition of IPv4 to V6 through dual stack. You were meant to complete this before we ran out of V4. That was the plan. You've obviously failed at that plan. And so the current plan that you're actually working through is from IPv4 to some weird hybrid life of NATs into another weird hybrid life of dual stack and NATs to eventually get you to V6. And currently the world is situated somewhere between points, well, I've got a laser, haven't I? NAT 4.4 only and dual stack plus NATs. And we don't know when it's going to exert fatal pressure on the NATs. We don't know how far you are going to push NATs. So interestingly, urgency has disappeared from this debate. Where what? 6 years after IANA ran out? No, it's 6.5 years. And there's still no urgency in this debate. I'm amazed. I am stunned. And the only reason you can put this down to is because of NATs. Because if you didn't have NATs, you'd be all running 6. We'd all be. There's no choice. So again, a fascinating development, completely unplanned. So we've bought at least 5 years, longer. But I would actually argue there's something else in NATs that we haven't really appreciated. And maybe we should, because of the relative role of names and addresses. There was this research group, name-based networking, that talked about the death of addresses, and we actually routed on names. Because quite frankly, you don't go to an address, you go to a named research, whether it's www.google.com or apnic.net or anything else. Why don't we route on those names? Why don't the packets have those names in their headers rather than addresses? What are addresses? You see, in NATs, The address isn't the address of the endpoint. That's a NAT table. The address is private. And a fascinating example of this is some of these latest web hosting companies or web caching companies, where when I put my content into them, my content no longer has a permanent address. When you ask to see my content, put it in a browser bar, the DNS will hand back the address of the closest data center. That's not the address of my content, it's the address of the data center. What actually delivers the content is the next thing you do. HTTP, I want to go to this site. So all of a sudden, the names are the things that distinguish the service, but the addresses are not service distinguishers. If they're not service distinguishers, what are they? I would actually argue they're session tokens. I borrow an address. I have a conversation. The address distinguishes my conversation from the myriads of other conversations at that time. But when I stop having that conversation, TCP/FIN, the address goes back in the pool for other folk to use. It's not a permanent identifier of me or you. They're ephemeral. We just borrow them. So maybe this is a step in a direction of networking that we always wanted to go to. This was always the dream, that what we didn't want was the fixed overheads of unique systems in both names and addresses. That's one too many. You either have unique names or you have unique addresses. You don't need both. The telephone was an exercise in unique addressing, and maybe where we want to be is an exercise in unique naming. The service name is much more important than the addresses. The addresses are merely just disambiguators inside the network. They're almost like those wacko virtual circuit MPLS tokens all over again, merely ephemeral tokens to separate one flow or the other. So maybe you shouldn't be saying NATs are evil, because they're not. You know, what keeps the Earth together? Gravity. What keeps the internet together? NATs. And you can say that gravity's evil or not, but in reality it's the physics, it just exists. And I would argue too that the only thing that keeps the internet together right now, recognise it for what it is, are NATs. We've grown from 2 billion to 20 billion devices, and now pervasive NATs are simply the fact of life. And maybe V6 is going to inherit this. We already see signs of this. If you're running a V6 stack, and from one of the major vendors here, you're using privacy addressing, which means that your real V6 address is actually hidden, the FFFE one, the one based on your MAC address, because that is a privacy leak. And that all of you effectively invent an address with the low order 64 bits and use it for a while and then migrate onwards. Do you have a permanent endpoint address? Well, in privacy addressing world, the answer is, well, no, you don't. You're merely borrowing an address for a while. So an IPv6 end address is actually ephemeral. Is name-based hosting here to stay? Name-based hosting is here to stay. So does IPv6 actually reproduce that 1970s architecture? I think not. We've moved beyond it, and we're never, ever, ever coming back. So if we're never, ever, ever coming back, why don't we just say it for what it is? Let's just do NATs in IPv6 and get over it. Because quite frankly, it's not a problem. We've already dissociated from fixed end addresses. We've already got private addresses. They're called ULAs. Persistent private addresses and NATs avoid that entire site renumbering nightmare that the IETF keeps on stumbling into every 5 years, going, how do we do multi-hosting? Well, the answer is NATs. It's the only one that scales. So you can do site multi-homing without route deaggregation. You can obscure your network details. You can do all the things that NATs actually do as positive in V6. So have I sufficiently disgusted you yet? Because as far as I can see, the V6 future is either going to embrace NATs, or there's going to be an awful lot of rethinking about whether V6 is palatable at all. So what's the message? NATs are good. That uniquely naming and numbering everything is economically infeasible, and no one wants it. The segmentation into clients and servers was actually something that the market wanted. We didn't want a peer-to-peer network. And we may not have wanted it this way, but the only reason why you have an internet today is because NATs actually do an amazing job at what they intend to do. So in some ways, they're just part of the architecture. Addresses are ephemeral, the names are really important, and generic aggregate addresses, yeah, we're pushing it up into the app area. NATs are now just part of our architecture. And maybe, again, that's what we wanted. We wanted to disambiguate location and service. Because the location doesn't matter, you're going to services. Are we over addresses? We might be. We might be over addresses. We don't need them the way we needed them in the 70s. I leave you to think about that. Thank you.
Thank you very much. Short question, please.
And one up the back too, Elaine.
Many countries require internet service providers to track the origination of packets or the destination of packets from the internet. Now, if each client has a unique address, maybe they have NAT inside of their network, but you know who the traffic is coming from or going to. Once you get into 10,000 to 1 NAT at the carrier grade side, is it practical to log all of that?
You know, there is this theory out there, again, that came from telephony, that the network knows everything. So all the law enforcement agencies went off to the ISP's door saying, tell us what users are doing. In the 1970s, it was possible to do that. Now, when I use multipath TCP, when I use NATs, when I use protocol agile NATs, when I use something like Chrome that basically encrypts everything, when I use the DNS inside HTTPS, anyone who thinks that the network can tell you anything about users is on psychotropic drugs. It just doesn't work like that anymore. If you want to find out what users are doing, you actually need to get on the other end of the encryption point. Sad fact, but true. So yeah, it's not the 1970s. That old technique of running over to the ISP and wanting the ISP to tell you what the users are doing no longer works. Tough. That's just the world we're built.
Hi, Alain Durand. Two comments. The first one is, in the 70s I was not there, but in the 80s I was. And we had multiple people behind an address. I was working at university. We had thousands of students on the mainframe, but at one IP address. So this notion that an IP address uniquely identifies a user is a novelty from the mid-90s, when we started, as you mentioned, to have dial-up. Before that, an address was multiple users. And we were just fine with that. Not as just recreated that state.
Totally agree with you, Elaine. I mean, this idea that somehow the IP address has to rat on us and tell other folk what we're doing is a fiction. And it just isn't something you can use.
My second comment is to your later point about maybe the address don't really matter anymore. I'm looking at the very interesting development in transport protocol, especially with QUIC. And what those things do, apparently, and I may be wrong, but they seem to create a session layer, an ephemeral session layer. And everything is really, your identity is tied to this session layer. It's not tied to your IP address anymore. And you can change your IP address as many times as you want. You could even go from an IPv4 address for 5 packets and then shift to an IPv6 address for the next 10 packets. And nobody will care, because what matters, what identifies you, is the session layer. So it seems that we are moving up the stack here in terms of what identifies somebody and what is really unique in the internet.
QUIC is a brilliant protocol. I wouldn't actually say that part of it was, if you will, invented by QUIC, because it borrows from an earlier protocol called HIP, the Host Identity Protocol. The idea was really fantastic. When you and I talk, we exchange session keys and make a long 64-bit number. And we keep it down in the encryption layer so we don't expose it. Every time a packet comes to me that contains that session key, it came from you. I don't care what IP headers were on it. It just doesn't matter anymore. It's you because it has that value. So QUIC has used this because that's the way you bust through NATs and you bust through address agility. As long as it has that session key, it doesn't matter what the from address is. I know it's from you. Nice thinking. It's a brilliant and I think insightful view. Because all of a sudden you don't care about NAT binding times and you don't care about that creativity of UDP. So yeah, QUIC is one of those revolutionary protocols. Good to see it out there.
Okay. Thank you very much.
Thank you.
Thank you all of speakers. The information is very important for the future network operation. Thank you for attending. The session of this session will be closed. Thank you very much. Could you